Okay, so let's do number 11 now. And here we have a region inside. Oh, yeah, so we've got two spheres. Right. Yeah. Okay. So this is another art challenge. I'm going to draw this by going through a sequence of pictures. The first picture is not going to be good. But the first picture is going to tell us, it's going to give us the hint that we need to draw the next better picture. And very often that's how things go. Is a failure that shows what went wrong with its strategy is actually a minor success. So that's about to happen. So let's see here. The first sphere there is a sphere of radius 5, centered at the origin. All right. So that's at 5. All right, the next sphere is a sphere of radius 5. Oh, that's nice, same radius, but it's centered at 6 on the x-axis. So it's centered about there and has radius 5, so it's going to be kind of like that. And this is a terrible picture. I can't see what's going on there because there's stuff in the way, right? But it gives me enough, though, that I can start thinking three-dimensionally about, okay, well, I've got two spheres that they're kind of intersecting kind of like this. Well, kind of like you get one sphere and you've got another sphere, but they intersect they overlap. They're not like totally overlapped. Like the centers are outside of each other, but they overlap, kind of to some extent. Mm-hmm. So we want to talk about the region that's inside both of those spheres. So I claim that that's going to look like, now I'm going to take a totally different point of view here. This having told me what to think about with my hands, which I can visualize three-dimensionally, I'm going to now look at it from over here. Right? I'm going to draw so from the point of view where I can most conveniently see the XZ plane, and from that point of view, well, I've got, let's see here, there was this one sphere, like that, of radius 5. Then let's see, the next one was centered at 6, radius 5. So the intersection is going to be something kind of like that. And then, of course, they intersect actually on a circle. Right, so this is kind of a, what does that look like? It's like well, gosh, I'm trying to think of something real physical that looks like. It's like a wheel, kind of like sort of one of these jelly donut kind of things, maybe, except it's got a rim to it. It's kind of like a UFO, maybe. It's a UFO turned on its side. Yeah. All right. Okay.
Is that a flat surface or is it? It's like football-esque. Yeah,
kind of. It's not long and skinny. I mean, this is actually this little belt going around the sort of over the top and bottom is actually a full circle.
Yeah, that's what I'm asking.
You know what I mean? So in other words, if I were to
the circle's just
as seen from this direction, it looks like it's kind of a round. It's fully round like that, and it just kind of sticks out a little bit this way and a little bit that way, and like.
Yeah.
So I think UFO is the best I've got physically. Yeah. So anyway. Okay. So what to do with this thing? Well, you can think about different ways to slice, etc. One thing is very clear: we don't want our first slices to be perpendicular to the x-axis, because then we're going to be slicing right through that edge curve, and that's clearly not going to be good. Everybody see why that's bad? Okay. What I'm going to do is, thinking just about the shape, let's think about projections again. Again, I'm a fan, right? I think this projection trick is a cool trick. And I want to project this thing that way. In other words, that way into the YZ plane. Yeah. So if we project this into the YZ plane, then note that projection is just a circle. Now, projecting in a different way, it's going to be some strange little, sort of, well, some sort of weird shape. But into the YZ plane, it's just a circle. And in fact, it's not even a bad circle. I can solve for the radius of that circle by looking at the algebra for these two original spheres. You've got x squared plus y squared plus z squared is equal to 25. And then you have, x minus 6 squared plus y squared plus z squared equals 25. Note that these things intersect. This circle where they intersect happens halfway in between the two centers. That's at 3 because that other center was at 6. So if you plug in x equals 3 into both of these equations, that turns into a 9. This also turns into a 9, and what you get is y squared plus z squared is equal to 16. So what you have is a circle of radius 4.
You plug in x equals 3?
I plugged in x equals 3 because these two spheres, if you look at where these two spheres intersect, they intersect halfway in between the two centers. And this center was at 0, x equals 0. This center was at x equals 6. So they intersect where x is equal to 3. So this whole belt around the sort of that edge, that whole belt is where x equals 3. I just plug that in and gets this.
Okay, so to solve for another equation.
Yeah. So once you have this, you know what the projection looks like. Now, again, it's almost over at this point. Dy dz on the outside, z goes from -4 to 4, y goes from negative square root of 16 minus z squared to positive square root of 16 minus z squared. It's our usual game with the circles there. And then what about dx? Now this, you got to be a little careful with this. The x bounds are not quite trivial because you got to solve for x in both of these equations. In both cases, there's a square root because of these squares here. And so you got to think about which square root. Do you take the plus or do you take the minus? So let's start with the lower bounds. And my picture is already kind of too muddy, so I'm going to have to redraw my picture again. And this is the nature of the beast, by the way. I mean, very often with triple integrals, I go ahead and sacrifice a tree in the name of math and draw plenty of pictures, make sure they're nice and big, give yourself plenty of space. If you have to draw, we're now on our 4th picture here, or 1, 2, 3, one more coming, 4 pictures. If you have to draw 4 great big pictures and use 2 pieces of paper for one problem, it's okay. So I've got this thing over here. Its projection over here is a circle of radius 4, and I need to know 4 given values of, let's see here. Oh, sorry. Given values of y and z. Yeah, so I'm looking at it again from this sort of from this point of view, where the y-axis is going into the page, and this is from this angle. In other words, sorry, from that point of view. Yeah, so the z-axis is still up. So I want to know what is x for given y and z. In other words, I need to solve for x on these two different spheres. Well, for this lower bound, remember that's part of this larger sphere. And on that larger sphere, you're going to get 2 values for x. There's the x with the plus on the square root, and there's x with the minus. The x with the plus on this larger sphere is this one over here. That's what you would get if you use the plus on the square root when you solve for x on this sphere. So you don't want that one. You want this one. So in the algebra, when you solve for x in this equation, take the minus on the square root. So let's actually do that, by the way.
Okay.
Yeah, so just to get it down here, let's see, we have x minus 6 quantity squared plus y squared plus z squared. is equal to 25. Therefore, x minus 6 is, let's see here, plus or minus, what are we going to do about that? Square root of 25 plus plus y squared plus z squared. So therefore, x is 6, and I got to decide plus or minus this square root. And, well, the plus would give me this point way over here. I don't want that one. I want the one there. That's going to be the minus. So, therefore, minus there. Is that cool? Okay, so this bound here is 6 minus that great big radical. Okay. Now, for the upper bound for x, well, that's part of this sphere like this. When you solve for x as a function of y and z, you're again going to get two different values of x. And you want this one, yeah, so you want the positive one there. So this is going to be, of course, just positive square root. There is no 6 or anything there. Oh, sorry, just like that. Cool? Yeah. No, yeah, sure, absolutely. And that's so exercises are sometimes you have to see it done, and then. So the question is not would you have gotten it yourself. The question is if something like this comes up on the exam, do you think you'll have a chance at it? And I think you will, right? Because the point is you get to look at this, look at all the pictures that I drew. I went through 2 full sheets of paper here. That's a lot of paper for one problem. And go ahead and do that on the exam if you have to. See it from different points of view. Think about the different strategies. Here we use projections, right? Not every problem will, but sometimes you do. Okay. Any other questions on this one before I kill it?